Okay, so topic 3.2, we're going to be talking about a little bit more in depth about enzyme catalysis. You should see the root in there of catalyze, right? These speed up chemical reactions. First, we got to talk about metabolism, or what metabolism is. Metabolism is simply all the chemical reactions required to sustain life. Kind of a generalized term. So yeah, the chemical reactions of life. That's what metabolism is. It involves forming bonds between two molecules. You might remember that from when we were talking about, biomolecules and sugars and things like that. And the fact that I know this is a terrible looking sugar, but you know, these end up in long chains sometimes. Uh, Starch or even these disaccharides. This is a terrible drawing, but disaccharides, things like sucrose or something like that. These have to be built from monomers, right? From monomers. Ah. And that's how you get these polymers. Well, polymers are what happens in this process of forming a bond between molecules. Of course, we know that happens through dehydration synthesis, which is the synthesis polymers typically. These are considered anabolic reactions. Anabolic reactions. I remember this because I think of anabolic steroids. Sorry for my bad handwriting. I guess over the break I've lost some of my dexterity. Anabolic steroids, which build muscle, right? You might have heard of your athletes, your favorite athletes building muscle like this. Anabolic steroids. These are anabolic reactions. Also, in our metabolic processes, we need to break bonds for energy and things like that, and components for other bond formations and some other reactions. This is formed through hydrolysis, which is the addition of water to break a bond, right? I think we forgot to talk in dehydration synthesis. Dehydration synthesis here. This is the removal of water to form a bond, right? Something you should remember, but okay. The addition of water to break a bond is called hydrolysis, right? You'll see this often in digestion when you're taking these sucrose molecules or sugar molecules and you're breaking them down into their component parts, right? So that they can be broken down even further for energy, right? For energy. So this is hydrolysis. Occurs in digestion. It's a catabolic reaction. I remember catabolic because if any of you have cats, they tend to break stuff up, right? Terrible cat drawing, but like, they tend to rip stuff apart with their fearsome claws, right? So catabolic reactions break stuff down. Break down. And typically, we're going to have catabolic reactions which are coupled with anabolic reactions. So these kind of go hand in hand, right? When we talk about metabolism in the body or in any organism. So let me all this stuff here. See even my beautiful cat down there, just to kind of show you a visual image of what I'm talking about. So on the left here we have an anabolic reaction, and again this is a very, very simplistic model here, but you can tell. Sorry, I'm taking a while to erase all this. You have some smaller molecules. You have the addition of energy, which is very important, right? You have the addition of energy. And these molecules are built into a larger molecule or a polymer in many cases. In many cases, this is going to be some sort of polymer. And in a catabolic reaction, you have a larger molecule, which is broken down into small molecules. Most likely, these are some sort of monomer. In many cases, anyway. It's not always the case, but in many cases. Broken down into monomers, and it also is precipitated by a release of energy, possibly for use in some cases for somewhere else in the cell. So these are anabolic reactions. Remember anabolic steroids, which build things, and catabolic reactions. Remember our kitty cat, which tears things down. So anabolic and catabolic reactions. Okay, let's talk a little bit about how these reactions relate to energy. Some chemical reactions release energy. These reactions are called exergonic. I remember that because I see these two letters, X, EX, and I think of energy exiting. The exiting of energy. The digestion of polymers, right? You'll find this, again, we talked about this in the last slide, but the breakdown of things to the component monomers, usually with the release of energy, typically through the process of hydrolysis. It's called catabolism. There's that prefix again, cat. Some chemical reactions require an input of energy. These are considered endergonic. You can think of that En there as energy ends up inside, or it's entering of energy. In other words, a storage of energy. These are built polymers typically, built through dehydration synthesis. This is called anabolism, as you might expect. So catabolism, anabolism, again, these are coupled together, right? They work hand in hand, right? Catabolic reactions and anabolic reactions are, are part of the same system in every cell. So, endergonic versus exergonic reactions. Exergonic energy release, it's in digestion. You typically will see this type of graph here where you have kind of a neutral zone here, and then above this you have how much energy you need to supply for this reaction to take place, and how much energy is released in this reaction. So you'll notice you supply a certain amount of energy, and then this reaction will spontaneously go to completion, releasing energy, right? And this is, you'll see this type of thing in ATP, right? You start with ATP, and you end up with products which are ADP, or adenosine diphosphate, plus an organic phosphate. And this is your product, and you have a release of energy in this scenario. This is how ATP works, right? You have an activation energy, and then you have a release. There's a release of energy when you release that phosphate, and it breaks down into its component products. That's an exergonic reaction. Endergonic reactions. Energy is invested. Energy is stored. You're going to find this in the synthesis of biomolecules. Even in the case of ATP again, right? Energy is supplied. And again, you would start off in this case with ADP plus an organic phosphate if we're going back to this example. And you would end up with the storage molecule of ATP, right? Storing energy in that phosphate to phosphate bond. If this product ends up on the top side of this graph, that means that energy must be supplied and that energy is kind of stored for release at a later date. So you can kind of see how these reactions can be coupled together. ADP is constantly having phosphates put back onto it so it can kind of spring load itself for this reaction over here in which this energy is released, right? So these reactions are coupled together. Enzymes work. So let's move this back into enzyme. The area you're talking about enzymes. Enzymes work by taking this initial reaction here and lowering the activation energy. If you can imagine you were a guy at the bottom of this hill for this graph right here, and you have a stone, you had to push all the way to the top. But once you got it up there, that stone would roll just fine all the way down and release this valuable energy down here, right? But it requires that activation energy, you pushing that stone all the way to the top before it can roll down to the other side. Now, if you look at this catalyzed reaction, you can tell that if you were to push a stone over this hill right here, it'd be much easier to push it over. But you really get the same amount of energy out at the end, right? You can see from graph 1 and graph 2. If you look at this neutral line down to the bottom, you get that same amount of energy out. In this catalyzed version of the reaction, however, it requires much less activation energy. So if you take one thing away from the notes in this video, I would like it to be that enzymes work by lowering the activation energy. So I put it in red. That's pretty important. So that's going to be it for enzyme catalysis. Join me in the next video for uh, our third topic, which is going to be environmental impacts of an enzyme function.